Bismillahirrahmanirrahim. In this module of convex optimization course, we will talk about geometric interpretation of duality. We will see the relationship between the Lagrange dual function and the objective function and constraint functions of the primal problem geometrically. So let's start. So we quickly recall that for a primal optimization problem, so with objective function f naught of x and m number of inequality constraint functions f1, f2 to fm, and we have p number of equality constraint functions. For this primal optimization problem, we can formulate a Lagrange dual problem in which we maximize a Lagrange dual function subject to Lagrange dual variable greater than or equal to 0, and that variable is associated with inequality constraint functions. So we have this formulation of Lagrange dual problem that we maximize g lambda mu. G lambda mu is a Lagrange dual function, and lambda and mu are Lagrange dual variables. So we also note that the optimal points are denoted by x star for a primal optimization problem and lambda star mu star for Lagrange dual problem. Okay, so to understand the relationship between g lambda mu Lagrange dual function and the functions of the primal problem, we take a very simple case. So we choose that we have only one inequality constraint and we do not have any equality constraint. So we consider a problem in which we have, say, we minimize f naught of x subject to f1 of x less than equal to 0. And again, this problem does not need to be convex. So we have one inequality constraint, and we have objective function f naught of x. And here x belongs to Rn, so we do not restrict x and the dimension of x. Okay, so for this primal optimization problem, and to interpret it geometrically, I'm going to define a set G, and that is a function of G set G in R2 and parameterized by two variables u and t, and we choose u and t such that f naught of x is equal to t and f1 of x is equal to u for every x that belongs to the domain of the problem. So D here is the domain of the problem. So this set can be interpreted as that you pick an x from the domain of the problem, and for each x we evaluate f naught of x, and we also evaluate f1 of x, and we form a pair ut, and we represent the point in ut plane. So for each x in the domain, we obtain a point in R2. So this can be interpreted geometrically as, say, this is the domain of the problem. So for each x belongs to the domain of the problem, so we map to this ut plane. So we obtain x, and we evaluate f naught of x, we evaluate f1 of x, and we obtain a point in this ut plane. Right? So we assume that all the points in this domain are mapped to some region of this ut plane, and let's assume that this region is noted by this ellipsoidal shape region in this ut plane, and we say that this is the set G we have, right? From this geometric interpretation, in fact, we can also evaluate the optimal value of the primal optimization problem. So first we note that all the points in the set G correspond to some x that belongs to domain of the problem, but we are interested in those points in the domain for which we have a feasible region in this ut plane. So if you see, we have substituted f1 of x as u, And in the primal problem, we require this f1 of x to be less than equal to 0 or u less than equal to 0. So that means, so we're interested in these points, and when u is less than or equal to 0. So when u less than equal to 0, we pick a point and the set G, say that we pick this point, and obviously this point corresponds to some x or multiple x in the domain D. And so we say that all those x are feasible for which f1 of x is less than or equal to 0, and that is by definition. So, and for all those x, we want to minimize f naught of x, and here f naught of x is indicated along this t line. So we say that for all points in the ut plane for which u less than or equal to 0, p star, the optimal value of the primal optimization problem, as the minimum point in this ut plane, right? And you can see here that the p star is, in this case, when u is equal to 0 and p star is given by this value. So will you minimize along this t axis, and we have this value is p star. So let's denote it with this point with p star. So this is a geometric interpretation of a primal optimization problem. Okay, let's relate this with the Lagrange dual function, right? So let's define the Lagrange dual function. Say the Lagrange dual function by definition is given by that we take infimum of the Lagrangian and we take infimum over the domain of the problem, right? So here f naught of x plus lambda f1 of x is a Lagrangian, and we note that lambda here is a scalar, so lambda belongs to R, and since we only have one inequality constraint function. Okay, so since we used a t to denote f naught of x and u to denote f1 of x, so let me substitute this in the formulation of Lagrange dual function. So what we obtain is so g of lambda as infimum of t plus lambda u, and instead of taking infimum over the domain of the problem, we take infimum over this set G in this ut plane. I can also write this Lagrange dual function in this form by taking a vector in this ut plane lambda 1, and I take an inner product of lambda 1 with a vector ut in this ut plane, and I take infimum over ut and over the set G. Right. So this can be interpreted as that for each lambda we obtain a vector in this ut plane, and we minimize the inner product of this vector with every point ut in the set G. This is equivalent to if you move in the direction of negative of the vector lambda 1, and you move as far as possible such that you remain the set G. Okay, so let me explain this geometrically. Say we take one point lambda 1 here. So let's say we want to evaluate Lagrange dual function for lambda 1. So we're interested what is the value of Lagrange dual function for this lambda 1. So we want to minimize the inner product of this vector with every point in this set G, right? So the idea is that we move in the negative direction of this vector, and we move as far as possible such that remain in the set. We say this hyperplane or this line indicates all the points for which the inner product with lambda 1 into with the point in ut plane is constant, right? And so we want to slide this green line uh, as far as possible in the direction of negative of this lambda 1 1 vector, such that we remain in the set. And we say that this is the maximum you can slide this green line in the direction of negative of this blue vector. Okay. And if we can also note that this line is given by simply t plus lambda 1 u, right? Because this is the inner product of this inner product, right? And we also note that the slope of this line is minus lambda 1. So the slope is given by, since the slope of this blue vector is 1 over lambda 1, and this is perpendicular orthogonal to this blue line, so the slope of this line is minus lambda 1. And we also note that when this line intersects with the t-axis, so here, so this point along t-axis give us the value of g of lambda 1. So let me denote this point with g lambda 1. So we take a point in ut plane. So we take a lambda 1, we take this blue vector, and for this blue vector we obtain this orthogonal green line, and we slide this green line such that this green hyperplane becomes a supporting hyperplane to the set G. And the point where this hyperplane intersects with the t-axis, that gives you the value of Lagrange dual function for lambda 1. So let me try to explain this in more detail, right? Say we take another point and we say we take this point lambda 2 1, and for this one, so this green is a supporting hyperplane, and this line is t plus lambda 2 u, and this point here, this is in fact the value of the Lagrange dual function at lambda 2. So okay, so this is g lambda 2. So we erase this one. Okay, so maybe we take another point, say in this on. So now we take a point in the second quadrant. So previously we took 2 points, and for those 2 points, so lambda was positive, right? So here we take lambda as negative, right? And we note that when lambda is negative, so this region, so this green hyperplane is a supporting hyperplane to this set G, and the value of Lagrange dual function is given by, say, this point here, and that is G lambda 3. So this is just a geometric interpretation of the Lagrange dual function. For each value of lambda, we obtain a supporting hyperplane to the set G, and for each value of lambda, we get the value of Lagrange dual function. So we note here that the maximum value of the Lagrange dual function can be, so this value, and in fact this is, for this example, so this is p star. So or we can say that the maximum value of the Lagrange dual function, which we denote with d star, would be equal to p star in this case, and therefore so for this example we have a strong duality. Okay, so let me explain this in more detail. If we take this lambda, so we call this lambda would be lambda star, because this is, for this lambda you can get the maximum value of g lambda. So g lambda cannot be greater than this value, because this is because we require to support this set G with the supporting hyperplane. So we denote this point with lambda star 1, and this is the line t plus lambda star u, and we have this point would be g lambda star. And since this is equal to p star, so we have a case of strong duality. We can also plot Lagrange dual function, right? So previously we took different vectors. So we took, so say this lambda 1, so somewhere here lambda 2, and somewhere here lambda 3, right? And so lambda 1, lambda 2 were positive, lambda 3 was negative, and for different values we obtained the Lagrange dual function. But the maximum value of Lagrange dual function would be g lambda star. So if I want to plot this Lagrange dual function, so what we obtain is, say we denote this value with p star. So, and we know that for some value, some positive value of lambda, g of lambda would be equal to p star, and we denote this point with lambda star. And for all other values of lambda, g of lambda decreases to minus infinity or decreases some value. So we note here that g lambda here is a concave function. The maximum value of g lambda cannot be greater than p star, and if g lambda star is equal to p star, we say we have a strong duality. In this example, we had strong duality. We may also consider a case in which we have weak duality. So let's consider one more example. So again, we assume that we only have one inequality constraint function, but the set G in this case is denoted by, is given by this arbitrary shaped region, and we call it G. Right? So where is P star here? Right? So we recall that, so we're interested in this region, because for these values of u, we have an associated x that is feasible, right? And over this region we want to minimize along t, and we note that, so this point, this is the minimum value of t for all negative u's or for all non-positive u's, right? So we say that p star is denoted by, so the value around, so this value is p star, right? Okay, let's talk about the interpretation of Lagrange dual function in this case, right? Again, we take some, say, lambda 1 point, and for this lambda 1 point, so this would be the value of the Lagrange dual function g lambda 1. Since for this lambda 1, the green hyperplane is supporting the set G, so this hyperplane is supporting the set G, right? So what is the maximum value of Lagrange dual function in this case? So we note that, so this is g lambda 1, so we can change lambda, and for different values of lambda we obtain different values of Lagrange dual function. But what's the maximum value we can have, or how close can we go to p star in this case, right? So this vector indicates the point lambda star 1 for which we have the value closest to p star, right? So we know that, so if we call this lambda star 1, and where this green line intersects with the t-axis, we call it g lambda star, and we had p star above this g lambda star, right? So in this case, the maximum value of the Lagrange dual function is less than p star, or we say we have weak duality, right? So we note that, so what is stopping us to have strong duality in this case? So this region, right? And in fact, so the region for which the x is not feasible, so that is restricting us, or that does not uh, allow us to have the maximum value of Lagrange dual function close to p star. So this is the interpretation of weak duality case. Since we are reviewing different notions, different concepts in duality geometrically, we can also look at the concept of complementary slackness, KKT condition. So we say we have two problems. Say in the first problem, the set G is given by this ellipsoidal shape. So we note here that the lambda star, or the value of lambda for which the Lagrange dual function has the maximum value in this example, is greater than 0. So we say lambda star is greater than 0. So the complementary slackness condition states that lambda I star times fi x star is equal to 0. It simply means when lambda star is greater than 0, fi of x star should be equal to 0. Or when fi of x star is less than 0, then lambda I star must be equal to 0. Right? So in this first problem, we have lambda star greater than 0. So this implies that fi of x star is equal to 0. And you can see this here. So what is fi of x star? So fi of x star, so this is the point. So here u is equal to 0, and in fact u is f1 of x. So the optimum value appears here when your u is equal to 0. We can say fi of x star is equal to 0. So let's take another problem. So in problem 2, we say we have the set G is given by this. So in this problem, we note that lambda star is 0, or in fact you can see that fi of x star, since p star is this value, so we know that fi of x star, or u, is less than 0. So the complementary slackness condition states that if fi of x star is less than 0, then lambda star must be equal to 0. So that is fi of x star less than 0 implies lambda star is equal to 0. And you can also see this geometrically, that for this value of lambda is equal to 0, we have the maximum value of the Lagrange dual function. Okay. So this was the geometric interpretation of different concepts in duality theory. We stop here and we will continue in the subsequent module. Thank you for your time.